Well, I guess I'll start with my thank yous. I want to thank the committee for letting me get my 10 or 15 minutes of fame, and also for picking the meeting to be in this city with which I've had a very long and very personal history. So I'm going to talk about spectropolarimetry of Cygnus A and Hydra A with the JVLA and some future prospects, not just for these sources, but other sources with the ngVLA and the SKA. So we use Cygnus and Hydra as exemplars of their classes. For those of you not hugely familiar with FR1 and FR2, Cygnus A is generally taken as the classic example of an FR2 radio galaxy. It is sharply bounded in its emission, has hot spots and a weak jet. Whereas Hydra A is an excellent example of an FR1, which has low brightness tails going off in great distance. The brighter emission is close to the center, stronger jets, and I'll show you a picture in a minute. The key thing here is that both of these sources are embedded in a deep magnetized and ionized cluster medium. The little chart, I'm not going to go through these numbers, show you some redshifts, distances. They're both very similar. They have a very useful scale of about 1 kiloparsec per arc second. They're both quite strong, especially Cygnus A. And as many of you will be aware, it is extraordinary high brightness, surface brightness of that source. And on the far right are some X-ray characteristics. On the upper part of the panel here is a nice 2 gigahertz color-coded picture from the VLA of Cygnus A showing its key features. And on the right side is the inner parts of Hydra A. This is only about 10% of the entire source structure. If you go down in frequencies, these tails just keep going and going and going, and they just sort of disappear into the intergalactic medium. This is, I didn't want to put in a picture of the X-ray emission of Hydra, didn't have it at hand, but this is typical for Cygnus A. The right panel shows the very extended X-ray halo of about 2 megaparsecs in size. The bottom right is the Chandra picture showing you the interaction of the shock waves of the emission of the X-ray driven by the expanding radio lobes, evidence for evacuation of the area due to the radio lobes, and on the left is an overlay of a 327 megahertz VLA picture showing you the relationship between the radio brightness and the X-ray brightness. So how did I get into this business? Well, being an early scientist at the VLA, we had unprecedented resolution, unprecedented sensitivity, and Cygnus A was well known for its anomalously low polarization at 5 gigahertz from early Cambridge work. It seemed that the VLA would be ideally suited to try and understand the origin of this depolarization. So some early papers that I did with John Dreher, Chris Perley, and Greg Taylor on Hydra A, we used 2 narrowband frequencies, because that's all we could do in those days at C-band, and 2 at X-band to try and understand the depolarization. Whether the origin is due to some galactic effect, whether the origin is due to some cluster effect, internal depolarization, there are lots of options. We did not answer any of those questions very well, but we found something very interesting, that both of these sources are embedded in their cluster halos are magnetized. The external cluster is magnetized at the level of 2 to 10 microgauss or higher if the origin is due to the shock gas around the lobes, and is highly organized over tens of kiloparsecs in scales. But the VLA was not sufficient to answer the fundamental question we were trying to understand, which was, is the depolarization due to internal depolarization due to line of sight through the source itself and intermixed thermal gas in the synchrotron gas, or was it due to some external effect? So when the JVLA came along, I was convinced to go back and revisit the whole thing all over again. And because now we had continuous frequency coverage due to this marvelous Canadian-built wide-R correlator. Thank you very much, Peter Dudney. And we had lower frequencies, because as you're going to see, it's the lower frequencies which are crucial to trying to understand the origin of depolarization and the interplay of gas in fields at these frequencies. So the little chart at the bottom shows you the observations on Cygnus and Hydra. Hydra's proposal was actually by Mike Bell, but he left astronomy, as many of you will know, and we inherited the project. Lorado Sebokolodi, my student, provided by Oleg Smirnov from South Africa, did all the beautiful analysis that you're going to see. She's now Baidoo, by the way, so the future publications by her under her married name. The details are seen on the chart. The point of the number of planes will come up here in just a moment. At this point, I want to point out that full spectropolarimetric imaging of a source like this is a pretty big deal. To avoid bandwidth and time attenuation and Faraday depolarization within the channels for a source of such high rotation measure, you need to have narrow channel widths and fairly time sampling. So these requirements required about 2,500 individual frequency channels for the Cygnus A and 5 to 20 second time integrations for that 66 hours of observations. And when you combine that with the approximately 3,000 individual separate spatial resolution elements at our chosen resolution of 0.7 arc seconds, and the reason for that will come clear in a moment, and 3 Stokes images, you have a pretty big data analysis problem. So to do the analysis, we generated, or Lorado generated IQU cubes for both sources at 2 resolutions, 0.75 arc seconds, which is the highest resolution you get at 2 gigahertz in A configuration with the VLA, and 0.3 arc seconds, and the reason for that will come clear in just a moment. Here are some beautiful pictures showing the polarization. Cygnus A is not a low polarized source at high frequencies. There's 10 gigahertz, 6, 4, and 2, and you will see that as you go down in frequency at constant spatial constant spatial resolution, it becomes increasingly depolarized, more strong on the left eastern lobe and a little less on the right. Same situation with Hydra, which is dynamically rather different. It's a type 1 source, fluffy and floating, and you get the same overall picture, but this time it's the lower southern source, which is depolarizing more quickly. This one has rotation measures as high as 10,000 radians per meter squared in the blue areas on the right. Now, the key way of doing this depolarization analysis is to make fractional polarization plots of all the 3,000 spatial resolved positions. On the left plot shows you the fractional polarization from one particular beam element at 0.7 arc seconds resolution on Cygnus, or maybe it's on Hydra. It's on Hydra. The middle is the polarization angle. The black is the native angle. It goes through 20 radians of rotation between 2 and 10 gigahertz. And on the right is the rotation measure transfer function. The red line is the rotation element. It's what you get if there was a single screen with no emission and a single rotation. And what you see is that there's lots of structure, and we do not have to do any RM clean here because we have such full and complete frequency coverage that we get the full picture without any other tricks. And the blue thing in the middle shows you the residual position angle after removal of the dominant term from the rotation measure. It's not linear. It fluctuates around, lots of gorgeous structure. So when you want to look at gorgeous structure, we've got 3,000 pictures to show you. Luckily for you, you only get 4 of them. On the left side are 4 different depolarization fractions. The middle are the rotation measure angles, and on the right are the Faraday depth functions done by Fourier transform. Most lines of sight have multiple patches. They all depolarize. There is nowhere that doesn't depolarize. Then there is smooth structure in the depolarization functions indicating smaller scale structures that we had not have resolved at 0.7 arc seconds, and you can know where I'm going next. This is Hydra A, and you'll see some of the fabulous depolarization functions there with multiple beating components. The basic characteristics I've already stated here. I'm not going to go and read all these things because I'm running out of time anyway. So let's go on to what we need to do better. The only way I claim that you can separate foreground cross-beam depolarization from internal depolarization due to the source itself is you have to resolve out the screen, which is causing you all the trouble. To do this, you've got to go down in frequency at higher and higher resolution until the polarization rises and plateaus. So in this particular plot on the right is one of many thousands of depolarization plots. I'm only showing you the nice one. The green, the red, the other colors, these are the polarization fraction as a function of resolution at 4 different frequencies. So the green is the highest frequency, up at 10 gigahertz, and there's almost no depolarization at all. As you go down in frequency, you see the polarization decreases. The bottom line is S-band, 2 gigahertz. And as we increase the resolution from 3 to 0.7, which is the best we can do at S-band, there is no change in the fractional polarization at all. And if you're trying to find out what the internal depolarization of the source is, you've got to convince yourself you've resolved out that screen. If the polarization does not increase and plateau at some resolution, you cannot convince yourself that you have resolved out the foreground screen, which is responsible for the great majority of the depolarization that we are seeing. So what do you do when you don't have enough resolution? You model. So we did some modeling. So we do have 0.7 resolution is the best we can do at S-band. And that's where all the action is, down these low frequencies. But we do have the high frequency data at 0.3 arc seconds at X-band and Ku band. And so we adopted a technique of determining the high resolution, high frequency rotation measure screen using this high frequency data where the picture is much simpler, and then use these values to predict the low frequency polarization and depolarization, and then match that against the real data to see if we're on the right path. So we fitted, using this expression that you've seen a couple days ago, for the P0 is the intrinsic high frequency polarization, the RM is the rotation due to the foreground gas, and the exponential term, it accounts for the depolarization due to unresolved structures. Never mind the rest of that. And this is what you get. For Cygnus A, the native polarization is almost entirely red, which is 50 to 70%. It is a highly polarized source. The middle one is the rotation, which is the rate of rotation of the polarization with lambda squared. This reproduces the results that Chris Corelli and I did many years ago, but expands it and is a much better image. And the bottom one is the new one. It's the rotation measure dispersion. It's the rate at which things are depolarizing within the 0.3 arc second beam that we use to make this. Hydra A gives the same picture. You get for free, of course, the intrinsic magnetic field orientations. There's no surprise here, and you've probably already seen these beautiful pictures that Lorano made, so I'm going to go on. We then take this high resolution, 0.3 arc second, 300 parsec screen generated by the high frequency polarization data, rotate it by the lambda squared of the frequency that we're trying to predict, smooth it out to the resolution that we actually observed, and compare that to the actual data taken at S-band. And these are the remarkable results that we get. I can do this. The top two are beautiful. The red is the prediction, and the black are the data. That apparent disagreement of that second panel down in the middle is not real. That's a 180-degree rotation. We just made a plotting error. It's an excellent fit. The bottom two are the more complicated areas where you get multiple patches interfering. And even though we don't get an excellent fit, what we can see is that the predicted depolarization from the modeling is always above that was actual. And what we believe is that we just don't have the resolution to see the screen well enough to do the prediction. So what's the connection to the ngVLA and the SKA? Perfectly obvious. It is perfectly clear from our work that we have not resolved out these screens, and therefore we cannot make any definitive statements about what fraction of gas depolarizing in the source is internal, or is in a shocked region, or is in the cluster. We know most of it's in the cluster, but the fun part is in the interaction, and we do not have the resolution and the sensitivity. The only way you can do this is to get an instrument with enough resolution at the frequencies at which this action is happening. And that's at S-band, and that's at L-band. So I had some fun making up a spreadsheet. I put in some sources that I know something about, or I know people who know something about. So there's some sources, and there's the brightness at 1.5 gigahertz. I picked that frequency because the SKA and the ngVLA will be observing in that area. The delta nu is the resolution needed to ensure you don't depolarize within the channel width required by the RM maximum. Some other numbers you don't need to care about. The purpose here was, how well can we do observing, not with 1,000 hours or 10,000 hours, as we just heard, but with merely 8 or 10 or 12 hours, something that's good on human timescales? And the answer is really good. This instrument, the ngVLA, will do absolutely fabulous Faraday tomography, and it has the power to uniquely separate these things. And finally, the second last slide, what about the SKA? Well, I wish it had a little more resolution. I mean, I'm going for factors of 10. I don't like factors of 2. That's not good enough. We need factors of 10. It's 4 times better than the VLA. That's really good. But the absence of bands 3 and 4 is an issue. So Phil, you got to get those bands in there in order, because it is the continuous uniform frequency coverage at the frequencies in which the action takes place that we need in order to sort all this out. So, in conclusion, these are fabulous instruments. But I don't want to wait 20 years. I'll be 95 years old by the time you guys think you're going to finish these arrays. So please hurry up and get the rest of those damn frequencies. Thank you very much.
So questions for Ray? Yes, Peter.
Bands 3 and 4 sound like an excellent way for the U.S. to get started in joining the SKAs on a small scale.
Well, I'm the wrong person to talk about that. Ask the man in the back.
Yeah, thank you. Very nice talk. So I have a question about the structure function or the property of the turbulence. So did you check any structure function, or did you check any
structure function?
Spatial correlation.
Okay, so that's all in Lorado's thesis. So I'm going to duck that, and she did all the good work. I should also point out that Jean Eilick is currently writing up the interpretation paper. The 2 papers I cited with Sebokolodi and Baidoo are observational papers, so they explain the methods and give you the results. Jean is busy heading up the interpretation, including structure functions, which is something that she's really into.
Yeah, I have a comment about the structure functions, because we did that for the supernova remnants and ran into a problem, and we solved it. And we realized that Robert Lang had solved it before us in a 2008 paper. So the structure functions of the diffuse emission are actually heavily biased by the beam smoothing. And
you mean the RMTF?
The RM structure functions.
Yeah. Which is why we need continuous coverage.
Yeah, but actually up to about 10 times the synthesized beam, the structure function, its amplitude and its slope is affected by the averaging. And you can read it in Lang et al. 2008, but we're about to publish a paper about that too.
Okay. Yeah.
Okay, time for one quick last one. All right. No, thanks, Rick.
Okay. Yep.